Okay, in this video we're going to continue by talking about the so-called laws of thermodynamics. And so thermodynamics is a word that's made up of two root words, thermo, which has to do with heat, and dynamics, which has to do with motion. So the word thermodynamics deals with the study of how heat moves. So it deals with the movement of heat. Now there are actually three different laws of thermodynamics, and these three different laws explain how heat moves from one object to another object. And so the first law of thermodynamics says this: when heat flows to or from a system, the system gains or loses an amount of heat equal to the amount of heat transferred. More specifically, the heat added is going to equal increased internal energy plus external work done by the system. And this is really a consequence of the law of conservation of energy, which says that energy can neither be created nor destroyed. So really, the first law of thermodynamics, that is essentially the law of conservation of energy with heat as one of the forms of energy. Remember, the law of conservation of energy says energy can neither be created nor destroyed. Well, if heat is a form of energy, that heat could be transformed into another kind of energy, or other kinds of energy could be transformed into heat. And so that's really what the first law of thermodynamics is telling us. And so here's an example of what we're talking about. So imagine that you have a piston, and in the piston is in a tube, and there's gas inside this piston, and you apply heat to this piston. So that heat energy is going to go into this chamber and it's going to heat up the gas. So what's going to happen is the atoms and molecules of the gas are going to speed up, they're going to be going faster, and that's going to increase their temperature or increase their kinetic energy. And so the internal kinetic energy of that gas is going to increase. But as the temperature of the gas increases, it could increase the pressure of the gas, and that could actually push the piston up. And that could cause work to be done on the piston. Remember, work is force times distance. So if the pressure from the gas increases and it applies a force to this piston and pushes it up, it could be work. Now, basically, what the first law of thermodynamics tells us is the amount of heat energy that you put into the system, you're not going to get more energy out than that. You're only going to have available the amount you put in. So some of that heat's going to go to increasing the temperature, some of it might go to doing work, but the total amount of energy is conserved. That is what the first law of thermodynamics tells us. So again, what we have is that when you have heat flowing into a system or out of a system, the amount of heat energy, that's what that system has to work with. In other words, if I put heat into the system, that's how much energy is available to that system. And that energy might go into doing work, like moving a piston. It might go to increasing the kinetic energy of a gas. But only the amount of energy that I put in with my heat, that's the energy that I have to distribute into these different things. Now, the second law of thermodynamics, we just saw that the first law was conservation of energy. The first law of thermodynamics is conservation of energy. The second law tells us about the direction in which heat will flow. And it says heat never spontaneously flows from a cold substance to a hot substance. So, as an example, if you're talking about in the summer, heat's going to flow from the hot outside air into the cooler interior of a dwelling. That's why if your house is cool in the morning but the sun comes out and it gets hot, the inside of your house is going to warm up because the heat is going to flow inside your house. Your house is cool, the outside of your house is hot, the heat's going to flow inside your house. In winter, the opposite is the effect. As the outside gets colder, heat will flow from the warm inside to the cold exterior. Now, you might ask yourself, is it possible for heat to flow the other way? And the answer is yes. The key word up here is spontaneously. Heat never spontaneously flows from cold to hot. It always flows from hot to cold. So heat will always flow from hot to cold unless you do work. If you add energy to the system by doing work on it from some other source, then the direction of heat flow can reverse, and you can actually have heat flow from colder to hotter. That's how an air conditioner or a refrigerator works. There are pumps and coils that compress the air in ways that remove energy from the house and dump it outside, or remove energy from the refrigerator and dump it outside, and that causes the interior to cool off. But your refrigerator, your air conditioner, they're plugged into the electrical system of your house. There's energy going in to move that heat from cold to hot. Otherwise, without that extra energy, without that work being done, then the energy is always going to flow from hot to cold. Then there's the third law of thermodynamics. No system can reach absolute zero. The problem is, if I have a system and I want to, I've got a box and I'm cooling it down and I'm going to cool it all the way down to absolute zero, well, what happens is the heat from outside that box is going to flow in and spoil my efforts to cool it off. So the colder it gets, the more heat's going to flow into it. And so you can get really, really close to absolute zero, but it gets harder and harder the closer you get, and you can never actually reach it. So that leaves us with the third law of thermodynamics, which says no system can reach absolute zero. Okay, here is a quick question to help us kind of understand this idea. So the question says, when a hot cup is filled with cold water, the direction of the heat flow is A, from the cup to the water, B, from the water to the cup, C, random, that means it could go either way, or D, there is no heat flow. And the answer is, obviously, it's going to be from the cup to the water, part A. And the reason we know that is because heat always flows from hot, and so the cup is hot, to the water, which is cold. And of course, if it was reversed, if you had hot water in a cool cup, the heat would flow from the hot water to the cool cup. But in this case, we have a hot cup, we put cool water in, so heat flows from the cold water into the hot cup. And so what that means is that the water will warm up a little bit, and the hot cup will cool down a little bit. And eventually, they'll reach an equilibrium temperature where they come to the same temperature. Now, there is another concept that's related to the second law of thermodynamics called entropy. And entropy is defined as it's a measure of the disorder of the system. So a more disordered system has more entropy, or a higher entropy. Whenever energy freely transforms from one form to another, the direction of the transformation is toward a state of greater disorder, and therefore toward one of greater entropy. That means that when energy flows from one system into another system, if it does so spontaneously, it's always going to tend to create more disorder and higher entropy. So we can actually restate the second law of thermodynamics in terms of this concept of entropy, which is a measure of disorder of a system. And restated, we could say the second law of thermodynamics says natural systems tend to disperse from concentrated and organized energy states towards diffuse and disorganized energy states. That means that disorder tends to naturally increase. And so, in other words, energy tends to degrade and disperse with time, and the total amount of entropy in any system tends to increase with time. So this is related to the flow of heat, but basically the idea is this, that over time systems become more and more disordered. There's sort of a classic example of this in physics. So if you have a box and you have a partition in the box, and on one side there's a bunch of gas, and the other side there's no gas, there's just vacuum, then if I remove the partition, if I take this partition out so that it's able to open up, then what's going to happen is that the gas is actually going to flow to the other side. And that creates more disorder because the gas is spread out more. There's more places for the gas to be. Now, what the second law of thermodynamics tells us is that the reverse is never going to happen. You're never going to have a box with gas flipping about and have all the gas congregate on one side. And so you could never have all the gas move to one side, creating a vacuum on the right side and a bunch of gas on the left. They'll spread out more, but they'll never come together in such a way as to create a more ordered state. So here's another example to check our understanding of this concept. The question says, your garage gets messier each week. In this case, the entropy of your garage is increasing, decreasing, hanging steady, or non-existent. And the answer is increasing because your garage is just over time getting more and more messy. Now, you can, as an outside agent, go in and clean up your garage and make it more ordered. But you have to do work as an external agent to do that. So that's not a spontaneous change. And so this is sort of the idea. Entropy always tends to increase unless there's some external agent doing work on the system or providing energy to the system. In that case, you can actually increase the order of things. And so, for example, in my box that's got gas all over the place, I could put a vacuum on this side and suck all the gas over there and then put my partition, and I would have moved the gas to a more organized state, but I would have to do work on the gas in order to do that. And so this is the idea. And that word spontaneous is very important in these ideas. Heat flows spontaneously from hot to cold. Entropy will spontaneously increase. But if you do work on the system, all bets are off. You can make it go either way you want. Now, we've said that heat and temperature are different concepts. Temperature is the average kinetic energy the atoms and molecules of a body has due to their motion, their vibrations, and their spinning and running around. The thermal energy is the total energy of all the atoms and molecules moving together and their potential energy as they're attracting and repelling one another. The heat, though, is the amount of energy that flows from one object to another object because of that temperature difference. And so we know that heat and temperature are related, and obviously we have a concept of hot and cold. But the question is, how are heat and temperature related? We've seen that they're not exactly the same thing, they're different things, but how are they related? And they're related through this idea of specific heat capacity. And what the specific heat capacity tells you is if I input a certain amount of heat, how much will the temperature change? And it turns out that that's dependent on what specific material you're talking about. So if I put a certain number of calories or joules of heat into a block of brass, the temperature is going to increase a certain amount. If I take that same amount of energy and put it into a block of lead, the temperature is going to increase a different amount because the specific material is different. And so when we want to connect how heat is going to change temperature, we do it through what's called the specific heat capacity. And the actual official science definition of specific heat capacity is it's defined as the amount of heat or the quantity of heat required to change the temperature of 1 unit of mass of a substance by 1 degree. In other words, how much heat is necessary to change 1 gram of a substance by 1 Celsius degree. And some objects have a higher specific heat capacity, and sometimes that's just called specific heat. But if you have a higher specific heat capacity, that means it takes more energy to change your temperature by a certain amount of temperature. So every substance has its own specific heat capacity, and this can lead to different effects. And so the classic example is you have a hot pie in the oven, and you take it out of the oven, and you cut yourself a piece, and you touch the crust with your finger, and it's like it's warm, but it's not like hot. And so you take a bite of the pie, and you burn the inside of your mouth. And the reason is because the crust and the pie filling have different heat capacities. So in the oven, they're both raised to the same temperature, 350 degrees Fahrenheit or whatever the recipe calls for. But it takes a lot more energy to make the pie filling go up to that temperature than it does to make the crust. And so when you take them out of the oven, the pie filling has a lot more heat energy contained in it than the crust does. And so the crust will cool off much faster than the pie filling. And so that's why people tend to burn themselves, because they touch the crust and the crust is cooled off, but that pie filling has got so much heat still stored in it that it's got enough heat to burn your mouth. So let's check our understanding of this idea. Here we have a situation. Sunlight is shining on water and land, and the water increases to 20 degrees Celsius and the land increases in temperature to 25 degrees Celsius. And the question is, which has the higher specific heat, water or land? Now, in order to answer this, you have to assume they're getting the same amount of sunlight. So if they're getting the same amount of sunlight, but the temperature of the water goes up less, that means it takes more heat energy to change its temperature, and it has a higher specific heat capacity. And so that means that water would be the answer. That's what would have a higher specific heat. So another thing that happens when you put heat into a material is that material will tend to expand. And this is called thermal expansion. And most materials, when you heat them up, they get bigger. And the reason for this is because of the rise in temperature, the molecules are jiggling back and forth faster, and they end up moving with more energy, so they move further apart. So you've got a low temperature, the thing's just jiggling back and forth, and then you increase the temperature and it just starts really jiggling back and forth faster, and that means that things tend to spread out more. The atoms and molecules are moving in bigger swings, faster swings, and so the material expands. Now, the reverse is true when things are cool. When things are cooled down, they start to contract. And so I have a couple of examples here. Railroad tracks closely laid on winter days expand and buckle in the hot summer. And so when you're building things that have metal in them, you want to give them enough room to expand or contract, otherwise they can break. Another example is if you have a jar and the lid of the jar is on too tight and you can't get it off, one of the things that you can do is run the lid of the jar under the hot water tap. The hot water will heat up the metal of the jar lid, and the jar lid will expand, and that'll make it looser, and then you'll be able to remove it from the jar. Now, one thing that is interesting is the behavior of water as it freezes. Normally, when things get cooler, they shrink. But actually, at a certain point, as water cools and freezes, it actually increases in volume. And that's because of the way that the ice molecules orient themselves. They connect in such a way, and you can see in the picture here, on the left we have water, and all the atoms and molecules are sort of jumbled together. And as they freeze, they line up and they form a structure. And in that structure, there's a lot of space inside. And that actually makes the water expand as it's freezing, and it actually takes up more volume as ice than it does in the liquid state. This is very backwards compared to most materials. And interestingly, that's why ice floats. I mean, normally, if I have a bunch of lead and I heat it up until it melts, so I've got liquid lead, and then I drop just a piece of regular lead in it, that regular lead is going to be more dense and it'll sink. But if I have a glass of water and I put an ice cube in it, that ice cube will float to the top. And the reason it does is because it takes up more space and it actually is less dense. That's very unusual. So in this slide, it basically tells you about the expansion of water. And this occurs between 0 degrees Celsius and 4 degrees Celsius. And remember, 0 is where it actually freezes. That means it becomes solid. So when it's at 4 degrees, it's still liquid, but it's on its way to freezing as it gets cooler. Now, normally, as the temperature increases, it would expand, but the reverse is true with water. And what's really interesting is that when water is at that 4 degrees Celsius temperature, that's when it is most dense. That's when it has the smallest volume and the biggest density. Remember, density, usually represented by rho, is mass divided by volume. And so as you make the volume smaller, the mass doesn't change, the density gets bigger. And so that occurs at 4 degrees. Now, when water is actually frozen and becomes ice at 0 degrees, that's when it has the largest volume and the lowest density. And so that's because as the bonds form, they take up so much space, as I showed you in the previous slide, that they make ice is just much less dense than liquid water. In this slide, we can see an application of these principles. Now, the idea is this. I've got this big lake here, and it's in winter, so it's getting very, very cold, and outside the temperature is minus 10 degrees Celsius, and so that's really, really cold, and you would expect the water to cool down and freeze. But what happens is very interesting, because remember, when water is at 4 degrees, that's when it's most dense, and denser things will sink. And so as the water cools down, it becomes more dense and it sinks. the sinking will continue until the entire pond is 4 degrees Celsius. So as the water gets colder, when it gets to 4 degrees Celsius, it will sink to the bottom. And any water that's warmer than 4 degrees is going to float to the top. But it's subjected to this 10 degrees Celsius, and so any of the warmer water at the top is going to get colder. And eventually, the entire lake will chill down to 4 degrees Celsius. That has to happen before any of the water can become lower than 4 degrees Celsius. And as it gets colder from 4 degrees, the 4 degrees is the densest, so it's going to stay at the bottom, and it actually gets colder at the top. And so that's why the ice will form at the top of the lake. And so the ice is going to float and form at the top of the lake. And so that's why, for example, you can go ice skating on a pond in the winter, because the ice doesn't form inside, it forms on the top. Now, if you have a pond that has ice on top and water underneath, if the pond's deep and you go down to the bottom, you're pretty much guaranteed that water is going to be 4 degrees Celsius. And this is something that's very, very important, because the ice has to form only after the entire lake has been cooled down to 4 degrees Celsius. And so that takes a tremendous amount of heat energy being taken out of the water for it to cool down. And so it's very, very hard to freeze something like an entire lake, because you have to cool the entire thing down to 4 degrees first. And what that means, what that tells us, is that fish are going to be safe underneath the ice, because the entire pond is not likely to freeze, because it doesn't freeze all the way through, it freezes from the top down. And that takes a long time, and generally it just doesn't happen because the lake is so much water. It would take so much coldness to freeze the whole thing that there's just not enough time for that to happen. And so hopefully that makes sense. It's kind of a cool thing, literally cool and figuratively cool, but that's how ice forms, and one of the reasons why ice is a little bit different from other materials.